this is going on page 55 when we're done. So we're looking at models again. So remember, your models are your regression models, something that we are using for our data. So throughout this course, we will have many opportunities to work with and create models based on a given data set, which we've done a lot already with different types of data. Three particular important ones are linear, quadratic, and exponential. They are the ones that occur most frequently in the real world, so that's why they are important to us. But what is also important to us is what is on the AP exam, okay? On the AP exam, students will be expected to determine which model is most appropriate given a set of data. Okay, so you might think that they both kind of are good, or all three or whatever, but which one is the most based on all these different things that we can use to figure out that information. So we've looked at a few different strategies. And we've also talked about in the last few days that a quadratic and exponential curve can look similar, right? If you're just looking, especially if you don't have a ton of data, they can look very similar to each other. And so got to look at how can we figure out which would be a better fit rather. If you're familiar with statistics, or because I've mentioned it a few times, we can use R and R squared. So I've pointed it out because it's there in Desmos and because it is a good thing for you to understand. However, we are not doing that in this course. Okay, so that's why I've said don't use your R values to determine anything. You can look at them and be like, oh, it makes sense that they are this or that, but that's not our use for determining anything. Okay. All right. So what we have done when we had just pure data that we knew that came straight from a function and the numbers were beautiful and worked out real nice, but now we have like more real data, so it's not as pretty. We're still using kind of the same thing. So for a linear model, when the data reveals a relatively constant rate of change, okay, we should have exactly a rate of change, but relatively, okay? I mean, that's what we get with real numbers here. So the first thing we look at is, do we have equal length input value intervals? Yes, we do, okay? Then we can look at, do we have a relatively constant rate of change? So here, these differences would be 1.6, 2.4, 1.4, 2.3. So they're not crazy close, but they're relatively close enough. And if you look at the line of best fit there, you can see that they're just, those points are just right on either side of the line. Good? All right, so then we use a quadratic model when the rates of change are increasing and decreasing at a relatively constant rate. That's the whole symmetric idea. But we really just look at, does it generally follow a U-shaped pattern? So here's I still have my equal input value intervals, but my outputs, they decrease to about 2.1. I do not know that my minimum is 2.1, and then they increase. Maybe it is, maybe it isn't, but it's probably pretty close to that, right? And then exponential model, when the output values are roughly proportional, okay? Roughly proportional. Each successive output is approximately the result of repeated multiplication. So again, equal length input value intervals. 0.5 times 2 is 1. 1 times 2 is 2. That's about 1.9. Times 2 is about 4.2. Times 2 is about 8.8. So you can see that you have that repeated multiplication there. Okay, everybody good? None of that's new and exciting for sure. All right, flip that over then. We've talked about residuals a little bit. We're going to talk about residuals and errors together, okay? Because they are the same thing, just opposite. And so they're easy to get backwards. We got to make sure we can keep it all straight. So here is your y minus y hat. So your y hat here, that is your prediction that's on the line. Here's my actual y value right here, right? And so y minus y hat, my actual minus my predicted, is what gives us our residual right there. And then this talks about the deviation. That's more statistics stuff. We don't even need to worry about that. We don't need to worry about the line. We just need to worry about the hat. Okay, so when we create a model, because we've created a model, we can use our model to predict values for the dependent variable, give it an independent variable. I'm going to say the word predict a bazillion times because it's important that you remember. I think that's what this says. When using a model, it is important to remember this is only a predicted value. Okay, it's a prediction. We don't know for sure that that's what's going to happen. Okay. So then, if we use the input value from a known data point to find a predicted output using the model, the difference between the actual output and our predicted output is the residual. That is what we already know, right? We already knew that it was residual equals actual minus predicted. Old news, wrap, right? Then this goes on to say that the difference between the predicted and the actual is the error. So the error is the difference between the predicted and the actual. So you would get the same number, but the sign would be different on it. So it's not really the same number, but I think you know what I mean. So residual, actual minus predicted, that's RAP. Error, predicted minus actual, that is EPA. Everybody good with that? RAP and EPA, keep those straight in your head, then it's really not that big of a deal. It's very easy to do, but it's also very easy to overthink and then do something backwards. Okay, so then residual plots, which we looked at quickly, didn't do much with it, but recall that a regression lines are lines or curve that just fit the data. So again, this is going to be very repetitive, but that's okay. A residual value is the measure of how much the regression curve vertically misses the data point. What is the distance off of the actual curve? You take the actual and subtract the predicted. So actual minus predicted, that is your residual. So remember that a residual plot, here is my predicted curve. So that orange, that is my y hat. Okay. The points you see, those are my actual data that I was able to use to make that curve. Now, it's really hard to see. You can't really read these numbers, I don't think, at all. But I'll kind of explain them as we go. I can't read them either, and it's fine. But so to create a residual plot, you take your curve, whatever it is, and that orange line, that orange curve that I have now is going to be flattened out, and it's going to become my new x-axis, okay, or my new horizontal axis. This is my y hat now. Ooh, that was weird. So the vertical axis on the first one, that is my actual output value. The vertical axis here now is the distance those points are from the actual curve. And just like over here, all of these output values are positive. Since this is above my x-axis, these are positive, these are negative. Okay, well, we give you positive residuals, negative residuals. That is a residual plot. Okay. And if I have, so these are my actual values, right? I'm gonna put little A's here for my actual values. Right, and then these are my predicted values. So if I do actual minus predicted, that's what gives me a positive residual value. That means this line or my curve that was over here is under those points, so that line is an underestimate. So if you have a positive residual, your curve is an underestimate. And if it's negative, then it's an overestimate. Okay. And there are times when you might want something to be an overestimate or an underestimate. If you were trying to estimate how much food you need for, Thanksgiving when your family comes over or whatever, would it be better to have an overestimate or an underestimate? Overestimate. You don't want anybody mad because they didn't get any food, right? And everybody loves the leftovers, so there you go. All right. So then we have the difference between the predicted and the actual is the error. I don't know why we talk about both, because I don't think you even talk about both in AP Stats. I think you only talk about residuals. And But whatever. It says depending on the data set and context, it may be more appropriate to have an underestimate or an overestimate. That doesn't necessarily have anything to do with error, but error is predicted minus actual. Ooh, I spell error correctly. Had an error in my error. All right, so then it says the line of best fit will either give an overestimate or an underestimate, right? So here, again, these are my, I didn't put little a's here. These are my actual values as well. So if I do the predicted minus the actual, then when this is an underestimate, that will be negative, okay? So see how it says underestimate? This actually will be negative for underestimate. And positive for an overestimate. And I think that's the reason for this next phrase that I don't necessarily agree with, but it says, note, because it is important to note that the residual and error are very similar and often used synonymously, but they are not the same, right? The signs are going to be different. There is a difference, and then it says the sign of the error tells you if the prediction is an overestimate or an underestimate. Well, I think the sign of the residual does too if you just understand how they work. I also don't think it's the best idea for you just to remember by the signs, because since we do have to talk about both and we have to understand both, do you see how easy it would be to get them backwards and then start thinking about it and overthinking it and then just be confused because y'all are good overthinkers? That's what happens, right? So I'm gonna give you a different way to think about it so you don't have to necessarily worry about learning it with the signs, because that's just a lot of the same makes it confusing even when it's easy. Instead, I'll show you as we do this kind of how I want you to think about it and how it'll work for you, especially if you, if we talk about this and 5 minutes later we do it, you're like, oh yeah, it was positive or negative. If you didn't just talk about it and you have to answer the question, you need a way to dig it out of your brain, right? That's what I'm trying to get for y'all. All right, so let's look at example 1. A high school student is getting ready for basketball season and getting extra practice before school. Each morning he records the number of practice shots he took and records how many he made. The table above represents his recording. All right, so it says find a linear regression curve. So go ahead and type this into Desmos in your table. Find your linear regression. Notice that we've got shots taken, which are T, shots made, which would be M of T. There's not an X or a Y anywhere in sight. Don't be a Melissa. Okay. No offense to any Melissas out there. It was just the first name that popped in my head last year for some reason. And I didn't have a student named that, so I figured I could use that. If I end up with a student named Melissa, I got to find another name. Maybe I'll let Melissa, but yeah, it needs to be a boy's name. You're right. Okay, let's see. Let me get mine up here. Oh, mine refreshed. Okay. Sorry, I'm standing there because I was like, oh, I already have mine typed in, and then it's gone. So, well, maybe, no, it won't come back. That's fine. Whatever. It just takes me longer to type over here. Oh my goodness. Yeah, see, this is why I like to have them saved, because it's better if I don't use this. Oh my God. Okay. 20 and 126. Okay. That was rough. All right. So then we'll do our linear regression. And there is our answer. Okay. And let's write that down. So this should be M of T equals 0.41681T. minus 8.70101. Now, this is a regression. It is a prediction. We should have a little hat on the M of t, okay? But I will be honest with you, okay, because on the AP exam, if you don't have the little hats, they're not going to count it wrong. Because this isn't a statistics class, is my assumption why. But I still feel like it's my responsibility to teach it to you correctly. Plus, if we had never looked at the hats, the Y hat up at the top of the page really wouldn't make any sense. So it is a good practice to keep doing that. And I want you to know what it means. But if we leave it off, it's not the end of the world. Okay. All right. Everybody good with that linear regression? Okay. So now it says use your model in part A to find the error at t equals 50. All right, so error is what minus what? Predicted minus actual. Okay, so that means my predicted would be m of 50, so that has the little hat on it, minus m of 50. You see why it's important to have notation that distinguishes between the two? Otherwise, it's m of 50 minus m of 50. So there's reasons for the notation. All right. Then in Desmos right now, we don't have the function defined as m of t. We have it in terms of x and y because it did it all for us, which is fine. We need to use the m of t stuff over here. But since I don't have that here, me putting anything with m's and t's wouldn't make sense. But I can just say x equals 50. And then when x equals 50, here is my point right there. Okay, well, 12.13. 12.13959. And then I'm going to subtract what? 20. Okay. So then go ahead and do that. Subtract it. Is that what you got? No. Yeah, exactly. You got negative 7.86041. All right. Now, the reason that I have this one written down is because last year at this point, Desmos was not giving us 5 decimal places. It was only giving us 4, and that's what I had written on my paper. But this is one of the reasons why I'm telling you to write down 5 decimal places, because truly you should never, ever, 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 ever type back in a number that's not exact without saving it. But there's not really a great way to save it in Desmos. And a lot of times it doesn't matter because there's other ways to do things. But with things like this, if Desmos had, rounded or whatever, you tried to round and rounded wrong, good Lord, I don't know how to round, then things would turn out bad. So if we write down 5, like y'all wrote down 5, or actually I wrote down 5 here. I wrote down 4 last year. This is the answer I got last year. This is the answer I got this year. I only have to be correct to 3 decimal places. And or would we both be correct to 3 decimal places? Yes. What if I got this and you got this, then we both tried to round through to 3 decimal places? Would we have gotten the same number? No. Don't round. Truncate. Because some of y'all also do what I call domino rounding, which doesn't even make any sense. And then you swear to me some teacher taught you that, and I know that's not true. So just truncate. Just write it down and stop. Use 5. Just trust me as we go through things. Okay? We good? Okay, perfect. All right, so then this says, is the predictive value an overestimate or underestimate? Now, I know you actually have the values there to look at, but I also want you to think of it this way. Here's my prediction line, right? So I have a point on my prediction line. My predicted value is 12 something. I don't even care what the decimals are. My actual value is 20, right? Is my line above or below that point? Below. It's under it, so that means the line is an underestimate. We don't care about being positive or negative because you could get that easily mixed up. Okay? And I'm showing you that because obviously you can see that 12 is less than 20, but you might not always have the data in that obvious of a situation. Okay. What questions do we have? Anything? Okay, great. Grab your second sheet of paper. This is also going on page 55 when we're done. These screenshots show you how to do the residual plot, which we've already done once, and I'm going to show you again. But that's there if you need to go back and look at it. But here's the thing. It's not so important necessarily that we know how to plot them, but it is very important that we understand what the heck they mean when we look at them. And I guarantee you this will be at least one question on your exam regarding this. So using a residual plot to check the appropriateness of a model. You're going to be asked, look at this residual plot. Do you think this model is appropriate? And you have to know how to answer that question. So we know that a residual plot shows all residuals for a set of data and can be used to help determine if a model is appropriate for a given set of data. So here's the super important part. If a model for a given set of data is appropriate, the residual plot should appear without pattern. That means it'll just look like a random mess. Random mess is good, pattern is bad. When you plot your data, like if I plotted data and my data looked like a curve, I would think, okay, it's probably going to be, quadratic or exponential, probably not linear. And that's a good thing if we can see a pattern with our data. But then when we look at the residuals, patterns are bad. Okay, patterns are bad for residual. So then it goes on to say, if we can see a clear pattern in a residual plot, then the model used for regression was not appropriate. Patterns are bad. Randomness is good. Okay. I would expect for the question that you see, at least one of the questions that you see, to kind of look like maybe these four would be your answer choices, and it asks you something like which one would be a good regression model or whatever. So here we have in a good residual plot, residuals exhibit no clear pattern. No pattern equals good residual model, or regression model rather. When you look at this, it just looks like a random bunch of points, right? Like you look up at the stars at night and you just see a bunch of stars in the sky. You don't go, hey, that looks like the Big Dipper, and you see some sort of pattern, right? You just look like random stars in the sky. In a bad residual plot, the residuals exhibit some type of pattern, such as a curve or a wave. Pattern equals bad regression model. So that first one, if this was my set of data, that might be good because I'd be like, you know what, that kind of looks like quadratic. But it's not the data, it's the residuals. Therefore, a pattern is bad. This one, it just looks like the points are trending up. So that's still a pattern. And here, this looks like, I don't know, an X or a chromosome or something. Okay, we see the difference in those? It's a very easy question if you can understand what you're looking at and what it means. Okay, we good so far? All right. So now again, this says, how do we know if our predicted line overestimates or underestimates our data? Use the residual plot of the data to complete these statements. Okay, so here we don't have actual numbers like we did a minute ago with the 12 and the 20. This represents my prediction line. It just got laid out to become my new x-axis. And these are positives, these are negatives. These are my actual points, so I'm just going to label them with A's again for my actual data, right? So if this is my actual data points, and it's up here, it's a positive residual value, right? So when the residual value is positive residual value is this, the line is where compared to the point? Over or under it? Oh my God. Under it. Sorry. The line is under the point, right? So the line, when you have a positive residual, is an underestimate. When you have a negative residual value, the line is over it. So that is an overestimate. Okay, we good with that? Does that make sense to you? Okay, you can literally draw a line and think about your point. Like little pictures like that sometimes can just help you wrap your mind around whatever it is that you're doing. Okay, we good? I'll take that as a yes. Flip it over. All right, so it says consider the following data set above. Use residuals to decide which model works best, linear, quadratic, or exponential. So refresh your Desmos, type in this set of data. I know I have this one saved. Bam, there's my data. And then we're gonna look at it. Now, this looks kind of quadratic-y, right? It also could look kind of exponentially, right? But we're going to look at the residuals, okay? So we're first going to, we got a linear regression, okay? That one comes up first. Now, when you graph a linear regression, it doesn't look terrible, does it, when you just look at it that way? I mean, it's not, I've seen worse for sure. But when we plot the residuals, so you can click right there under residual where it says plot, and you can also click the little magnifying glass so you just see the residuals better. What do you think of the linear now? You think it's a good one? No, because you see a quadratic there pretty well. Yes? Okay, so I'm going to say linear. I think we can definitely say linear is out. Okay. So then we can change this to quadratic. And then I can zoom in again. I mean, it's definitely less patterny than the linear one. And if you need to change the colors of your stuff, you can do that here if you can see them better, if they're red or whatever. I'm pretty sure y'all know to do that stuff. But or if they happen to be the same colors as your Y's. You can also turn those things, the other ones, off if you don't want to see them. But that helps me see this point, which I really couldn't see just a second ago. So it kind of looks like a zigzag, but oh no. Let's see. Let's look at exponential. I don't hate it. So let's look at exponential. I need to click log mode. Y'all didn't need to do that, but it's because I have mine saved. Now this one, do you think that one looks more patterny than the quadratic? Yes or no? And I really think that maybe you could argue it either way. Here's what I believe to be true for the questions that you'll actually get with pictures, is that you will have, if you have more data points, it would be way more obvious. I really believe that it would look more like these, where you have a ton of points, so it's a little bit more obvious if there's a pattern or not. But here, this really kind of looks like a function that we've graphed before, right? That kind of looks like an m, like one of our polynomials. And if I look between that and the quadratic, I think the quadratic is probably less patterny, even though I know it does go up and come down and come back up. I probably need to find a different example where you don't feel kind of torn between the two, because I do think you could probably argue it either way, right? But I do think overall here, I think we should go with quadratic. Am I even on the right? There we go. I think we should go with quadratic here. I'll make sure when it matters for you that you're not really having to make a difficult decision there. All right, so then we have the weight of the newborn babies. Okay, we've used this function a few times. So go ahead and type this data in while I read it to you. So the weight of the newborn babies can be modeled by a linear function for the first 4 months after birth. Selected values for the weight, W of T in kilograms, of a particular newborn baby are given in the table above, where T represents the number of months since birth. So it says, use the regression capabilities on your calculator to find the linear model for the weight in kilograms of this particular baby X months after birth. All right, now this one gives me T and W of T. And then in part A, it starts talking about X and Y. So I believe that on this type of question, whether you used X and Y or W of T and T, that both would be acceptable, because it's kind of using both, right? Nobody's trying to confuse you and trick you into anything. I'm just going to write mine in terms of X and Y. So once I see my data's over here, so it told me to use linear. There's my linear regression. And there's my equation. So let's go ahead and write that down. That would give me y hat equals 0.8x plus 3.34. Okay. Is what I wrote down correct? Yes. Are we sure about that? What if I was to tell you no? What? That's actually okay here. Or I could, even if I use W of T and T, good. Why? Yeah. They literally tell you exactly what to do, right? Now, that is what Desmos told me, but that's not the end all be all. This is actually what it asked me to write. Y hat equals 3.34 plus 0.8x. Will they be that nitpicky? Honestly, I have no idea. So is it worth the risk? No, just do what it says and you don't have to worry about it. Okay? I mean, all right, we all good? All right. So then it says use the model found in part A to predict the weight in kilograms of this baby at 2.5 months after birth. Okay, so that means I want W of 2.5 with the hat on it because it's a prediction, right? Now, again, in Desmos, I don't have this defined as W and T, so I'm not going to use W and T. What am I going to type in? X. So I'm not going to use W and T. What am I going to type in? T. Yeah, no. Sorry, that's not the right answer. Okay, so here is my X equals 2.5 right here. There's my point. Get 5.34. So this is 5.34 what? Oh my God. Yeah. kg. Thank you. Kilograms. Okay. Goodness gracious. Okay. Units. Units. All right. We all good? Okay. Then it says the actual weight of the baby. Actual weight of the baby 2.5 months after birth was 5.5. What is the residual? All right. So residual is what minus what? Actual minus predicted. So my actual is W of 2.5 minus my predicted, which is W of 2.5 with the hat on it. So the actual is 5.5. We subtract the predicted, which is 5.34. And what does that give me? Yep, 0.16 kilograms. And was that an overestimate or an underestimate? Here's my prediction. My prediction was 5.34, right? My actual was 5.5. That is an underestimate. Okay. It's okay. Are we all good? All right. So then it says, would a quadratic regression be a better model, and explain? So let's look at our residual plot. So I'm going to plot my residuals. I'm going to zoom in. Oof. Look at that. That's linear. Do you think the linear model is any good? No, that's like a perfect quadratic, right? So, and that's the residuals, which makes that bad, right? And because it looks like a quadratic doesn't mean that the quadratic would be good. Just so you know, like that's not a connection here. So like that's really not good. And so if I look at quadratic, I see less of a pattern, right? Especially, and if I zoom in, it looks like a pentagon, but that really doesn't mean anything. I guess technically, I mean, we only have 5 data points. It kind of goes up and down and up and down. But wouldn't you say that's less of a pattern than a straight up perfect quadratic? Absolutely. And so we would say here, yes, residual plot for linear model shows a clear pattern. Does that make sense to you? See how to make those decisions? Alrighty. Then you read example 4. See if you can come up with an answer. Check with your neighbors, see if they agree with you. Okay, let me read this. An exponential regression was used to model a data set. The residual plot for the exponential regression model is shown above. Which of the following is the best conclusion about the appropriateness of the exponential regression model based on the corresponding residual plot? That's a lot of words. But first thing I want to look at, okay, I look at this residual plot. Would you say clear pattern or really no pattern? I would say no pattern. That's pretty random, right? So if I look at my answer choices, it's saying either is or is not appropriate and pattern or no pattern. So I think we agreed with no pattern, so I can eliminate B and D, right? Is no pattern good or bad? Good. No pattern means it is a good fit. No pattern means it is appropriate. Your answer is C. Okay. We good? Questions? All right. All right. Good deal. Then we are done for today.